Hey, excited to be here at the inaugural PyCon in Athens. I'm a system engineer primarily, and not so much of a software engineer, but I've been a software engineer in a past life as well. My main focus is around system architecture, observability, and security. And as mentioned, I'm currently working at Elastic, building an observability product for practitioners on call. Why this talk? It's a common problem between data scientists, SREs, and every Pythonista actually, struggling with vast amounts of data of any kind, and tool fragmentation across several teams, different ecosystems, different pipelines, different tooling altogether makes it for a mess situation to deal with data. That situation amplifies delays on feedback loops, making time to insight increase. So what we'll cover in this talk is what is ESQL, new query engine and query language by Elastic, and how Apache Arrow powers speed and interoperability between systems. We'll go over how we can pull ESQL results natively into the data frames ecosystem in Python, and go over a live demo. Hopefully the demo boots will be nice to me today. We'll also briefly cover a little bit about Elastic's machine learning for unsupervised anomaly detection. So someone asked me how many query languages exist there for Elasticsearch, and I had to have a wild guess. I'd say 7 or 8, but then I started counting them, and they end up being something close to 11. Which is kind of weird if you think about it, because in the end, they all transpile at some point into the search query endpoint, which is a JSON interface where you can compose complex queries. It's said to be a very flexible API, and people love it, but it's not very intuitive when you're trying to write something on the get-go, and it's also very tough to synthesize queries on top. So it's also something that's not very familiar with folks working with data, where SQL tends to be the lingua franca of data analysis. So what is the ESQL? It's not just a query language, it's also a query engine, and we also provide a unified UI around the whole experience. That's super important. Because not being just a query language, not being just a spec that you can form your queries, but also having the capabilities of a robust query engine gives us several benefits and improvements and speedups and what have you. So key benefits: greater query speed overall. It simplifies the use of Elasticsearch. The API is much simpler. It gives the ability to get into the next steps and iterations of Elasticsearch as an analytical engine, and provides an ability for any practitioner using data to get faster into insights. So the query endpoint for ESQL does not require any translation or translation. The queries are parsed and optimized for distributed execution. The logical planner and physical planners optimize execution across nodes, and as an engine operates on blocks of data instead of a row at a time. Having the ability to completely control the engine within Elasticsearch gets us to a place where we can improve over time, coming up with several optimization on top. We have data to show that most common queries, if you use ESQL, are actually super beneficial because you outperform the underscore query, the underscore search endpoint. ESQL can operate on top of unstructured and structured data. You can think of it as a procedural pipe language. And if you're familiar with SQL, you will see that there are some SQL-like filter capabilities for data manipulation. So what does a piped query language means? We call it pipe language because it mimics the pipe philosophy from Unix, and also draws inspiration from languages you might be familiar with, which is SPL. Splunk's search processing language, Microsoft Cousteau, KQL, or Amazon's CloudWatch queries. So it's not an entirely new concept. It exists, but we think Elasticsearch delivers to the next level. At a very high level, the SQL syntax is just a source command followed by a set of processing commands piped by pipe, and you can chain as many processing commands as you'd like, really. Each processing command works on the output table. You can think about not in the physical sense, but logically on the output of table of the previous command. So an example SQL query looks like that. If you've used Elasticsearch and used the search endpoint, you understand that it's much simpler to write. You can reason about it much trivially. The source command from Apache Logs is just a data stream or an index pattern, and then you have a set of other processing commands leading to an output natively in Kibana. So with that, fine. You can work with ESQL, with Elasticsearch. You can use the JSON output and do whatever you need with it. But why Apache Arrow? Why does it come into play? Apache Arrow is a robust columnar memory format, enabling zero-copy operation, and also has a wide support in libraries for cross-language utilization. You may know it by Wes McKinsey, author of Pandas. It's used by Pandas, it's used by Spark, it's used in various machine learning frameworks and many other use cases. Recently, Elasticsearch added the capability to be able to stream ESQL results as Arrow inter-process communication with Arrow IPC. Some clear benefits with that is that you avoid penalties from serialization to deserialization, and also by being able to seamlessly integrate with Pandas, you get to avoid the overhead of instantiating JSON objects and converting them to data frames or NumPy entities. So if there is one takeaway from this talk, is actually this one-liner, a very simple way for you to query Elasticsearch with ESQL, ask it to produce an Arrow format, and then there's a very helpful toPandas function where you can also directly ask it to map into the Arrow data frame type. You can also use toArrow if you want to stay natively into the Apache Arrow ecosystem, but if you're working with Pandas, as most data scientists do, that one-liner is super handy. In the demo, we're going to go over the New York City taxis dataset, loading from a Parquet file format, and then loading into an Elastic Cloud serverless instance, and trying to do some rudimentary analysis with a Jupyter notebook, something that any data scientist should be familiar with, really. So let's go with that. By the way, the New York City taxis dataset is an open dataset that you can use and play around. There are many datasets like that. You'll find them in any benchmark blog post demo, and it's part of the nightly benchmark for most of the analytical engines. So demo time. Let's see how it goes. So you should be familiar with that interface. That's just a notebook. So we're going to go over the setup, connecting with Elastic Cloud, loading and ingesting the data set, and then seeing how we can provide some relatively complex SQL queries, get the Arrow, streamed Arrow format back to us, load it into Pandas, and then do some plots with Matplotlib, and try to think about how you'd go about it as a data scientist, an SRE, or data curious developer. So pretty simple requirements. I've already installed them. It's just the Elasticsearch client, Pandas, PyArrow, Matplotlib, and things to load Parquet and work with time. I've spun up an Elasticsearch serverless project for this demo. You can go ahead and create your own serverless project on Elastic Cloud. It's free for 14 days, and you can give it a go. gonna go over the data set, load it. You can ignore this boilerplate code, but it's just essentially loading the Parquet file, validating that there are results here with the head function, then going over creating an Elasticsearch index, and then if the internet is gracious, we're gonna be able to ingest the data. We're gonna give it some time. I've sampled the data to not be as large. It's like over tens of millions documents. I've truncated down to less than 100,000. Cool. Data is in. It's good. So that's the one-liner dimension. I use it every time. It's super handy. That's the two pandas lambda function. And then going over the core SQL queries and wanting to navigate the data set of the New York taxes data for the month of January 2023. So I'm gonna create I'm gonna construct a SQL query. That's my source command. Those are the commands that will actually produce the table, let's say, for the data. And then I'll get to sorting them per hour, getting to what's the percentile in minutes for each hour. Perhaps not the best of the name with this min suffix. Doesn't mean minimum, it means minutes. Sorry about that. Now that I say it, yeah, it's kind of weird, but you get the point. This is like a very rudimentary anomaly detection, like Pullman's anomaly detection. It's not an actual proper regression analysis or anything. It's just checks if something is if the P95 in minutes is over 2.5 times over the average duration. Let's call it an anomaly. Okay. That's not super robust, but you get the idea. Like if I increase that, you should be getting less results. Yeah. And then just one result. Okay, that's fine. Okay. So you can also slice and dice data. You can express new fields with the eval function. You can manipulate fields such as time. So in this query, I'm just gonna get the cost per ride, cost per mile, just to see if there's any outlier there. I'm gonna plot them later on to be more digestible, but you get an idea of the expressiveness of ESQL. I could remove or add any pipe and come up with slicing and dicing the data the way that that I want to explore it. And it's nice because you tend to synthesize a query just getting from the wider to the more narrow data set as you like. And you can iterate much easier than just the huge blurb of JSON that is the search endpoint. Cool. That's a fun one. We're extracting the hour of day and day of week, and then going over the total amount of trips and going over the tip rate. Let's see if there's some outlier there. You can also do bucketing if you are an SRE or any data scientist really. You tend to put data into buckets for further analysis. I'm doing some simple bucketing exercise here for you to see. Yeah. And that's the eval case in its simplest form, which is like pretty simply that we're evaluating the missing output column on a case basis, where if that statement is true, then we classify as a missing case. If it's not, everything is okay. In this case, all of our data set seems to be okay. So once we have all the data frames created, we can just pass them over to Matplotlib and get some insights. As you normally do, we can see like there is some anomaly obvious, like there's a huge spike at the end of the month where the P90 of duration in minutes just explodes. We can investigate later why that is. Yeah, let's see. The cost per mile, as mentioned earlier, as an hourly median plotted over there, or as a rolling window, to see if there is any anomalies. We can check the seasonality within the day. That gives you an idea of how trips fare over the span of a day. And then, simple stuff like the top pickup zones by revenue. Okay, standard stuff. So, okay, that's cool. We are able to almost completely abstract Elasticsearch and not pay the penalty of JSON serialization and getting that back into Pandas and NumPy. So that's pretty nice. But as mentioned earlier, it's not super robust alone for anomaly detection. So we're gonna go over and check pretty briefly some Elastic's machine learning capabilities now that we have the notebook open. So we're going to configure a job ID and a data feed ID for this data set. Ignore the boilerplate. I promise it's much easier than it looks. I just have this thing so things are interoperable for the demo's sake. Going to wait for some time for the jobs to load. And then we're going to create a data feed for the test. So essentially what we are doing here is we are creating a small script that will feed the data back to an unsupervised machine learning job from that index, from the start time to the end time, and try to check with some influencers whether there is an anomaly spotted. All right. We're going to start the data feed. It's going to take some time for data to be ingested from that index back to the machine learning nodes and do the analysis. So there's going to be some awkward pause here for a while as data is being crunched through the machine learning node. The results return. So we do have some anomalies detected. The record score is here pretty high. I think that it's a 1 to 100 type of thing, and there are some anomalous hours spotted. We're gonna plot them over here with a simple scatter plot diagram, and you can see like there are areas where things are anomalous thanks to Elasticsearch machine learning. And that's a stem plot. That's a more familiar way to represent anomalies in this context. And yeah. That was it. I'm not gonna tear things down because perhaps there might be some question. But some folks asked like how fast exactly is fast in this case. This is a super not scientific micro benchmarking around the JSON experience versus Apache Arrow versus mapping directly to Arrow D type into Pandas. So I'm gonna just set the same queries over a few times and then visualize the results. Less is better here. We can see that Arrow to Pandas with the Arrow D type is much more performant than JSON. Now you should understand that this is just it's not a great test. Obviously, latency to the Elasticsearch endpoint dominates these result sets. If you were to benchmark, you'd benchmark either locally or with a workload runner in a very close proximity to the Elasticsearch cluster to have some meaningful results. But you get an idea of the overhead. That's an average of 3 runs, and in every run, Pandas with Arrows is actually much more performant, and that's just with less than 100,000 documents. Imagine when you are going over hundreds of millions or billions documents, like the difference is staggering. We have benchmarks, and there are benchmarks available in Wes McKinney blogs around Arrow. Systems like Polar also use it, and you can see like how much more efficient this columnar in-memory format is. It's super great. Of course, you can also consume that information through Elasticsearch. For some reason, I'm not seeing right here, but it's should be there. There's a handy heat map that shows anomalous areas of interest based on some type of influencers over here. We're not going to go over that, but just give you an idea that you can actually try it out in just a few minutes with this notebook over to an Elasticsearch instance on cloud. So, with that said, what are some takeaways from this talk? We didn't go into details because I was afraid that the demo codes would fail me with a larger data set or data set that would be more impressive as a use case. But you can perhaps imagine that as an SRE, using this type of workflow, you can work with your colleagues and backtesting alerting strategies over real data. You might want to fine-tune service level objectives. It's very handy if you're doing like post-mortem analysis to go over data books and notebooks and explain your chain of thought, your thought process, and actually, reuse the notebook or, I think there are today like collaborative notebooks as well that can, use with your team. It's also super handy for capacity planning. You can run ARIMA models. We run ARIMA models for Elastic Cloud or seasonal ARIMA models. It's super, super handy. Also for data scientists, you can integrate into your existing data pipelines. And if you have operational data, for example, in Elasticsearch, hey, how about, use that type of way to lift and shift data and shove it into your machine learning or AI applications. In general, for every practitioner, really, by having the ability to use the data frame ecosystem natively, you can seamlessly integrate into your workflow. So Elasticsearch gets into your ecosystem. You don't have to buy into Elasticsearch. You get right into just by having the Arrow IPC as the interoperable format. Yeah. So lastly, takeaways. Elasticsearch query piped query language, a fast distributed search engine. It has a very expressive query pipeline. Arrow, you can use it everywhere. It's fast. PyArrow and Pandas are amazing. It works great for every SRE or data curious practitioner. And I've linked the resources for this demo in the slides. And with that, thanks so much. Open for questions.